Hello and welcome. I'm so glad you've joined me tonight. For a little while, we can set the world aside. The noise, the worries, the endless lists of tasks, and simply explore history and knowledge. Tonight, we will travel across thousands of years through time and history to discover the story of numbers. Numbers that shape our world, that make science, trade, calendars, and civilization possible. From the first marks on bone and stone, to the earliest counting systems, to the ideas that would one day become algebra, geometry, and beyond. Human beings have always needed to count. Before cities, before writing, before books or schools, counting was essential for survival. Early humans needed to know how many animals they had hunted, how many days had passed since the last full moon, how many people were in their family or tribe, how much food had been gathered. Even without written symbols, humans developed methods to track quantities. They used stones, sticks, bones, and marks on cave walls. One of the oldest known examples is the Ishango bone, discovered in Central Africa. It is more than 20,000 years old. It has a series of notches carved along its surface. The patterns suggest deliberate counting, possibly tracking days, objects, or simple calculations. Early humans also used one-to-one correspondence. One stone for one animal, one mark for one day. This principle forms the foundation of counting. Tally marks appeared independently across continents. In Europe, Africa, Asia, and the Americas, different cultures invented similar systems because counting is a universal human need. Counting helped humans measure time. The cycles of the moon, the sun, and the stars were recorded. Early calendars were created to track seasons. This was essential for agriculture and migration. Numbers were critical for trade. Baskets of grain were exchanged for fish, animal skins for tools. Fair trade required accurate counting. Scientific studies show that humans have an innate ability to perceive small quantities. This is called subitizing. Most humans can instantly recognize up to 4 objects without counting. Larger numbers required symbols and organization. Early civilizations developed their own counting systems. The Egyptians used hieroglyphs for numbers. The Sumerians developed cuneiform symbols for accounting. These were some of the earliest recorded numbers in history. In Africa, tally sticks were used for trade and calendar tracking. In Asia, notched bones and clay tablets recorded quantities. Even animals demonstrate basic quantity perception. Birds can distinguish 1 from 2 eggs. Wolves sense if rivals are few or many. Humans went further, creating abstract numbers. Numbers became separate from physical objects. This abstraction was a major step toward mathematics. Counting became central to agriculture. Farmers measured seeds, tracked harvests, and monitored rivers and seasons. Numbers allowed prediction, planning, and cooperation. Over thousands of years, practical counting evolved into written number systems. Symbols were developed to represent quantities. These symbols allowed humans to calculate, to build structures, to trade, and to record history. Every number you have ever used, every calculation ever made, every scientific discovery began with this basic human need to count and the development of abstract ideas about numbers. Early humans were laying the foundation for the mathematics that would shape civilizations for millennia. This marked the beginning of a journey through time where humans transformed simple tallies into complex systems, and numbers became a universal tool for knowledge, planning, and discovery. In the earliest civilizations, numbers became symbols, and counting evolved into writing. This allowed humans to record quantities, to calculate trade, and to organize complex societies. In ancient Egypt, numbers were essential for agriculture, commerce, and monumental construction. Hieroglyphic symbols represented units, tens, hundreds, and thousands. Farmers measured fields with knotted ropes, calculating areas for sowing and harvesting. Architects and engineers measured volumes of stone blocks and determined precise angles to construct pyramids with remarkable accuracy. The Rhind mathematical papyrus, dating to around 1650 BCE, contains over 80 problems, including division, fractions, and linear equations, revealing the sophisticated understanding Egyptians had of mathematics. The Babylonians developed a base 60 or sexagesimal number system. This system influenced modern timekeeping, dividing hours into 60 minutes and circles into 360 degrees. Babylonians used clay tablets to record calculations for trade, taxes, astronomy, and engineering projects. They created multiplication tables, tables of squares and cubes, and solved quadratic and cubic equations using algebraic methods. Their observations of celestial movements, including the planets Venus and Jupiter, relied on precise numerical recording, allowing predictions of eclipses centuries in advance. In ancient China, numbers were recorded using bamboo strips and clay counting rods. The 9 chapters on the mathematical art, compiled during the Han Dynasty, contains hundreds of problems, covering linear equations, proportions, geometry, and practical applications. Chinese mathematicians measured river flows, designed canals for irrigation, and calculated land divisions for taxation. They developed methods for calculating areas of irregular shapes and volumes of storage pits and granaries. These techniques influenced later Chinese astronomy, surveying, and engineering. The concept of zero emerged in India around the 5th century CE. It represented both a placeholder and the idea of nothingness as a number. This invention revolutionized mathematics, enabling the decimal place value system, simplifying calculations, and allowing the development of algebra and advanced arithmetic. The Bakhshali manuscript shows evidence of using zero in calculations, demonstrating its role in solving complex problems in trade, astronomy, and architecture. This innovation spread to the Arab world and eventually to Europe, forming the foundation of modern mathematics. Numbers were closely linked to astronomy. Civilizations observed the stars, tracking lunar cycles, solstices, and planetary movements. They recorded data using numbers, created tables for predicting celestial positions, and developed early calendars. The Babylonians, Egyptians, and Mayans independently designed systems to predict eclipses, determine the length of the year, and align agricultural and religious activities with celestial events. Trade was another driving force behind the evolution of numbers. Merchants needed accurate records of goods, weights of metals, volumes of grain, and prices in different regions. Clay tablets, papyri, and counting rods served as ledgers, tracking transactions over long distances. Numbers became crucial for taxation, loan agreements, and city administration. Geometry arose from practical needs, surveying land, constructing buildings, and dividing plots accurately required measurement. Egyptians used right triangles to survey fields after Nile floods, ensuring equitable land distribution. Babylonians measured slopes for canals and dikes, while Chinese engineers designed bridges, walls, and city layouts using precise measurements. Symbols were standardized to make calculations more efficient. Cuneiform numerals in Mesopotamia, hieroglyphs in Egypt, bamboo rods in China, and Indian digits allowed knowledge to be preserved and shared across generations. Numbers became tools for calculation and instruments for abstract reasoning. Mathematics was no longer limited to survival. It became essential for civilization, culture, and science. Astronomers used numbers to calculate planetary orbits. Architects used numbers to design temples and palaces. Engineers calculated forces, and merchants predicted profits. The concept of zero and place value enabled fractions, decimals, and algebra. This allowed the calculation of areas, volumes, and proportions, and laid the groundwork for geometry, trigonometry, and eventually calculus. In Mesopotamia, advanced methods were developed for solving quadratic and cubic equations. Egyptians used arithmetic to distribute bread and beer rations, and to calculate labor for construction projects. Chinese mathematicians solved simultaneous equations and used negative numbers in their calculations. In India, Brahmagupta formalized rules for arithmetic operations with zero and explored solutions for complex algebraic problems. Numbers were deeply intertwined with culture and religion. Calendars determined festivals. Sacred architecture reflected mathematical ratios, and rituals relied on precise timing. Mathematics became a language bridging trade, science, governance, and spirituality. Every calculation recorded on stone, clay, papyrus, or bamboo, from the simplest tally to the most complex algebraic problem, represents the ingenuity of human thought. Early humans transformed simple counting into a structured system, symbols and rules that allowed civilization to flourish. Numbers were no longer just marks on a surface. They were tools to understand the world, to predict events, to organize society, and to build lasting monuments of knowledge. In ancient Greece, mathematics became both a practical tool and a field of philosophical inquiry. Numbers were no longer solely for trade, construction, or astronomy. They were seen as fundamental to understanding the universe itself. Pythagoras, born around 570 BCE on the island of Samos, founded a school where numbers were considered the essence of all things. He and his followers discovered relationships in music, noting that the length of a string determined the pitch of a note in precise ratios. These observations led to the concept that numbers could describe harmony in the natural world, linking mathematics, music, and philosophy. The Pythagorean theorem, which describes the relationship between the sides of a right triangle, is one of the earliest examples of mathematical proof. It showed that abstract reasoning could yield universal truths, independent of measurement or physical objects. Greek mathematicians used logic axioms and rigorous proof to ensure conclusions were always true. Euclid, living in Alexandria around 300 BCE, wrote Elements, one of the most influential mathematical works in history. It organized geometry into definitions, postulates, and proofs. Euclid's systematic approach made mathematics precise, allowing scholars for centuries to build upon his work. He defined points, lines, and planes, and established the rules for angles, triangles, circles, and polygons. Greek mathematicians explored ratios and proportions, not just in abstract geometry, but in art, architecture, and astronomy. The Parthenon in Athens, built during the 5th century BCE, exemplifies the use of the golden ratio to create aesthetic balance and harmony. Sculptors and architects relied on precise numerical relationships to achieve symmetry. Numbers were also applied to astronomy. Greek scholars like Hipparchus and Aristarchus measured celestial distances, studied lunar and solar cycles, and used trigonometry to predict eclipses and planetary positions. Mathematical models allowed them to calculate the tilt of the Earth's axis and the length of the year with remarkable accuracy. Mathematics became a philosophical pursuit. Plato, a student of Socrates, taught that the study of geometry and arithmetic trained the mind to grasp eternal truths. In his Republic, he emphasized that understanding numbers and forms was essential to understanding reality itself. Greek mathematicians introduced irrational numbers. The discovery that the diagonal of a square could not be expressed as a ratio of whole numbers challenged earlier assumptions. This realization sparked debates on the nature of numbers and the limits of human understanding. The concept of mathematical proof became central. Unlike earlier civilizations, Greeks demanded that every statement be justified logically. This approach influenced countless fields, from engineering and architecture to philosophy, science, and later mathematics in the Islamic world and Europe. Mathematics in ancient Greece also intersected with daily life. Trade in Aegean ports required arithmetic, weight systems were standardized, and coins were minted with precise values to ensure fair commerce. Surveyors calculated land divisions, engineers designed aqueducts, and city planners used geometric grids for streets and public spaces. The study of numbers extended to recreational mathematics. Greek puzzles, magic squares, and geometric problems were popular, challenging both students and philosophers to think critically. Mathematics was not just a tool, but a means to cultivate the intellect. Greek innovations traveled widely. Through Alexander the Great's conquests, Hellenistic culture spread mathematics across Egypt, Mesopotamia, and India. Libraries like the Library of Alexandria preserved knowledge, allowing scholars to study, refine, and expand on earlier discoveries. The foundations laid by Pythagoras, Euclid, and other Greek mathematicians endure today. Their focus on logical reasoning, proof, and abstract thinking shaped modern mathematics, influencing algebra, geometry, calculus, and even computer science. From simple numbers for trade to geometry that explains the cosmos, the Greeks transformed mathematics into a systematic, rigorous discipline. It was no longer merely practical, but a language to describe reality, to uncover patterns, and to reveal truths about the world. The precision of Greek mathematics continues to resonate. Architects and engineers still apply Euclidean geometry, while astronomers rely on trigonometry and ratios discovered millennia ago. Music theory, visual art, and even modern physics draw on principles first formalized by Greek scholars. In understanding their work, we see how numbers evolved from tools of necessity into instruments of intellectual exploration, a bridge between observation, logic, and imagination. Every theorem proved, every ratio measured, every diagram drawn represents centuries of human curiosity and ingenuity. The story of Greek mathematics shows that numbers are not just symbols, but a way to perceive the structure of the universe, to predict outcomes, and to create harmony in both science and art. Roman surveying techniques were precise and systematic. Agrimensors used the groma to establish straight lines and right angles, ensuring roads, walls, and aqueducts were aligned correctly. The chorobates, a level with a water trough, measured inclines, allowing aqueducts to maintain a constant slope for optimal water flow. These techniques required careful measurement, fractions of a Roman foot were used, and calculations recorded in wax tablets for future reference. Land division was crucial for taxation and urban planning. The Romans implemented a grid system for newly conquered territories, known as centuriation. Each parcel of land was measured and mapped, divided into square plots of roughly 50 hectares each, with roads and irrigation channels calculated precisely. This mathematical organization supported agriculture settlements and military control across the empire. Roman engineering marvels relied on both arithmetic and geometry. Bridges, such as the Pons Fabricius in Rome, demonstrate accurate arch calculations. Vaults and arches distributed weight evenly, allowing constructions to withstand centuries of use. Amphitheaters, like the Colosseum, required careful planning of seating arrangements, entrances, and stairways, all based on modular arithmetic and geometric proportions. Even harbors, like Portus near Ostia, were designed using geometric principles to guide ships safely and efficiently. Trade demanded sophisticated numerical systems. The Roman economy relied on standardized weights, measures, and coins. Bronze, silver, and gold coins represented fractions of the denarius, allowing transactions to be precise. Merchants calculated quantities, prices, and conversions using Roman numerals and fraction tables. Markets in cities from Londinium to Alexandria maintained ledgers of goods, ensuring accountability for imported spices, grains, and textiles. Fractions were essential in daily life. Romans used uncia, a twelfth of a whole unit, to divide coins, food rations, and building materials. This system of division allowed merchants, soldiers, and artisans to operate efficiently. Mathematics was not abstract, but integrated into the rhythm of everyday Roman life. Education in mathematics was practical and philosophical. Children of merchants learned arithmetic, students of engineers mastered geometry, and elite Romans studied astronomy to plan festivals and public works. Texts, tablets, and abaci preserved knowledge, allowing successive generations to build upon the foundations of Greek and earlier civilizations. Romans also applied mathematics to astronomy and timekeeping. Sundials were carefully aligned using geometric calculations. The Julian calendar required accurate measurements of the solar year and the addition of leap days to synchronize months with seasons. Observations of lunar cycles and planets guided religious festivals and agricultural planning. Military campaigns depended on precise calculations. Engineers calculated distances for fortifications, angles for siege engines, and supply lines for armies moving across mountains, rivers, and deserts. Mathematical tables ensured that legionaries received rations and equipment proportionally, maintaining cohesion and efficiency over vast territories. Roman contributions influenced future civilizations. The combination of Greek theory and Roman practicality created a body of knowledge that endured through the Byzantine Empire and into medieval Europe. Surveying, engineering, and accounting techniques were preserved in manuscripts, used to rebuild cities and roads after the fall of the Western Roman Empire. Mathematics was also applied to architecture in monumental public spaces. The Forum in Rome was designed with precise proportions. Columns, porticos, and temples measured carefully to create harmony and functionality. Baths, theaters, and aqueducts combined utility with aesthetic proportions, all dependent on arithmetic and geometry. Roman numerals, while limited for complex calculation, were complemented by abacus tools. Merchants and administrators used counting boards with pebbles, performing addition, subtraction, multiplication, and division. These tools allowed rapid calculations for trade, construction, and military logistics. Trade networks extended across the Mediterranean and beyond. Roman merchants exchanged wine, olive oil, grain, metals, and textiles across cities in Hispania, Gaul, Africa, and the Near East. Numerical systems enabled accurate pricing, taxes, and inventory management. Mathematics became a backbone for commerce, supporting a sprawling empire with millions of people. Engineering precision ensured the longevity of infrastructure. Bridges and aqueducts remained in use for centuries. Roads facilitated communication and transport, and ports allowed fleets to navigate safely using geometric calculations. The integration of math into civil life reinforced the stability and efficiency of the empire. Roman mathematics was both practical and innovative. While borrowing heavily from Greek theory, Romans applied it to the challenges of empire, adapting abstract knowledge into functional solutions. Roman mathematics continued to influence architecture long after the fall of Rome. The Pantheon's dome remains one of the largest unreinforced concrete domes in the world. Its dimensions calculated to distribute weight evenly and maintain structural integrity for centuries. Builders relied on ratios and proportions, ensuring that columns, porticos, and interior spaces aligned perfectly with aesthetic principles and functional requirements. Road networks required precise measurements. The Via Appia, Via Aurelia, and Via Flaminia connected Rome with distant provinces. Surveyors measured distances using standardized units, such as the Roman foot, pace, and mile. Gradients were carefully calculated, allowing wheeled vehicles to traverse mountains and valleys efficiently. Roads facilitated trade, military campaigns, and communication, all dependent on mathematical accuracy. Roman aqueducts illustrate the application of advanced geometry and hydraulics. The Aqua Claudia spanned more than 45 miles, crossing hills, valleys, and rivers. Engineers calculated gradients, used arches and siphons, and ensured water flow was steady and reliable. Settling tanks were used to purify water, and distribution systems delivered it to baths, fountains, and private homes. Trade mathematics included conversions between local currencies. Merchants traveling from Gaul to Egypt needed to calculate prices in different denominations and record transactions accurately. Fractional units, such as uncia and scripulum, were used to divide coins, commodities, and taxes. Ledgers recorded grain, wine, olive oil, and metals, ensuring fairness and transparency. Weights and measures were standardized. Roman libra, amphora, sextarius, and other units enabled consistency across the empire. This standardization facilitated trade, taxation, and construction. Mathematics provided the framework for logistics and economic stability. Military campaigns depended on mathematical precision. Engineers calculated distances for fortifications, siege engines, and temporary bridges. Supply chains relied on accurate numbers of rations, weapons, and equipment. Tables and calculations ensured legions received provisions in proportion to troop numbers. Roman engineers were adept at surveying battlefields and constructing temporary camps using precise geometric layouts. The Julian calendar represented a major achievement in applied mathematics. It corrected previous misalignments of months and seasons. Leap years were introduced to adjust for the extra fraction of a day in the solar year. Astronomical observations guided festivals, agricultural cycles, and civic events. Education in Rome emphasized practical mathematics. Young Romans learned arithmetic, geometry, and basic astronomy. Merchants focused on calculations for trade. Engineers mastered geometry for construction. Elite students explored abstract theory, preserving knowledge for future generations. Mathematics also underpinned Roman law and administration. Census records, tax assessments, and population counts relied on numerical accuracy. Officials calculated land values, assessed levies, and managed public funds, ensuring the empire functioned efficiently across continents. Roman contributions laid the groundwork for later civilizations. Surveying, engineering, trade mathematics, and astronomy influenced Byzantine and medieval European knowledge. Manuscripts and Abbasid preserved numerical methods, allowing scholars to reconstruct Roman techniques. Architecture, roads, and aqueducts became templates for future urban planning. Daily life depended on arithmetic and fractions. Rations of grain, olive oil, and wine were divided using uncia fractions. Coins were counted carefully for transactions. Merchants, soldiers, and citizens relied on mathematics to maintain order and fairness. Scientific observations advanced through measurement and calculation. Roman astronomers recorded lunar cycles, star positions, and planetary movements. Sundials and water clocks measured time, while calendars synchronized civic and religious life. Mathematics in Rome was not abstract. It was deeply embedded in practical life. From surveying and construction to trade, taxation, and astronomy, numbers guided the empire. The precision and organization of Roman mathematics allowed civilization to thrive and left a lasting legacy that shaped Europe for centuries. Through roads, aqueducts, coins, and architectural marvels, the influence of Roman mathematics endured. Techniques were adapted and expanded, providing the foundation for future engineers, merchants, and scholars. By integrating Greek theory with practical application, the Romans created a system where mathematics was a tool for efficiency, durability, and progress. From monumental architecture to the administration of millions of people, numbers were the invisible force maintaining the empire. Trade, military logistics, education, architecture, and astronomy all depended on Roman numeracy. Each calculation, each measurement, contributed to the stability and prosperity of one of history's most influential civilizations. Roman numerals may have limited complex computation, but the use of counting boards, abacai, and tables allowed sophisticated calculations, enabling long-distance trade, engineering, and administration to function smoothly. The legacy of Roman mathematics extends far beyond the empire's fall. Surveying methods informed medieval land divisions. Engineering principles guided bridge and aqueduct construction for centuries. Trade mathematics influenced commerce throughout Europe and the Mediterranean. Numbers in Roman society were practical, pervasive, and enduring. They connected people, managed resources, and structured daily life. Mathematics was integral to civilization itself, a tool for organization, innovation, and progress. Through careful observation, calculation, and application, Romans ensured their empire could sustain millions of citizens. The roads they built, the aqueducts that flowed, the trade networks that spanned continents, all relied on the unseen structure of numbers. Mathematics was embedded in law, architecture, trade, and military logistics. It allowed Romans to build infrastructure, administer territories, and observe the heavens. The practical genius of Roman numeracy influenced countless generations, shaping the world in ways still visible today. Roman engineering, astronomy, commerce, and administration demonstrate that numbers are not merely abstract, but vital instruments of civilization. The careful use of arithmetic, geometry, and measurement allowed the empire to thrive and to leave a legacy that endured for millennia. During the early medieval period, following the decline of the Western Roman Empire, much of Europe experienced disruption in centralized education and record-keeping. However, the Islamic world emerged as a hub of intellectual activity. Scholars in cities such as Baghdad, Cordoba, Cairo, and Damascus preserved, studied, and expanded the knowledge of ancient civilizations. The House of Wisdom in Baghdad became a center for learning and translation. Texts from Greece, Rome, India, and Persia were meticulously copied and translated into Arabic. Mathematical works, including those of Euclid, Archimedes, and Ptolemy, were studied and analyzed. Arabic numerals, derived from Indian mathematics, began to replace cumbersome Roman numerals. This positional decimal system allowed for faster computation, efficient record-keeping, and more complex calculations. Al-Khwarizmi, a scholar in Baghdad during the 9th century, wrote influential works on arithmetic and algebra. His book, often translated as the Compendious Book on Calculation by Completion and Balancing, introduced systematic methods for solving linear and quadratic equations. The term algebra derives from the Arabic word al-jabr, meaning completion or restoration. He provided practical techniques for solving inheritance problems, trade calculations, and land measurements. These methods were not purely theoretical, they were applied to administration, commerce, and taxation. Geometry continued to develop, building upon Greek foundations. Islamic scholars studied Euclid's elements in depth, proving theorems and extending them into new areas. Mathematical diagrams illustrated architectural designs, irrigation systems, and celestial models. Geometric methods guided the construction of domes, minarets, and mosques with precise proportions and symmetry. Patterns of tiling, known as zellage, reflected advanced understanding of symmetry, angles, and repetition. Astronomy and mathematics were closely linked. Accurate timekeeping was essential for religious practices, including prayer times and the direction of Mecca. Observatories, such as those in Moraga and Samarkand, recorded the positions of stars and planets. Mathematical tables calculated planetary motion, eclipses, and lunar phases. Trigonometry, both plane and spherical, was developed to facilitate these astronomical calculations. The sine, cosine, and tangent functions were refined and applied to problems of navigation, surveying, and construction. The Islamic world also innovated in practical applications of mathematics. Trade required conversion between local currencies and calculation of profit margins, tariffs, and taxes. Agricultural surveys used arithmetic and geometry to measure fields, calculate water distribution, and allocate resources efficiently. Engineering projects, including aqueducts, bridges, and city walls, relied on precise measurements and calculations. Al-Kindi, another prominent scholar, wrote extensively on arithmetic, geometry, and cryptography. He explored the properties of numbers, the use of proportions, and techniques for encoding and decoding messages. These studies influenced not only mathematics but also early forms of security and communication. Education flourished in Islamic cities. Madrasas and libraries preserved knowledge and made it accessible to students. Mathematics was taught alongside astronomy, medicine, and philosophy. Students learned the decimal positional system, multiplication and division methods, and problem-solving strategies. Abbaci, counting boards, and numerical tables were widely used as teaching tools. The translation movement was critical in transmitting knowledge to Europe. Latin translations of Arabic texts introduced algebra, the decimal system, and advanced trigonometry to medieval scholars. This knowledge spread gradually through Spain, Sicily, and other points of contact between the Islamic and European worlds. Fibonacci, in the 13th century, studied these texts and introduced the Hindu-Arabic numerals to Europe in his book Liber Abaci. These numerals eventually replaced Roman numerals, revolutionizing European computation and commerce. Mathematical discoveries during this period were both theoretical and practical. Equations were solved systematically, ratios were applied in architecture, and astronomy guided navigation and religious practices. Measurement, calculation, and observation formed the backbone of intellectual and technological achievements. The Islamic world also developed magic squares, combinatorics, and early probability. Magic squares appeared in manuscripts, reflecting patterns of numbers arranged in grids so that sums of rows, columns, and diagonals were equal. These mathematical explorations had cultural and philosophical significance. Combinatorial methods were used to calculate inheritance, solve logistical problems, and explore numerical patterns. Trade networks across the Mediterranean, India, and East Africa relied on precise calculation. Merchants used arithmetic to determine currency exchange rates, shipping costs, and weight conversions. Mathematics enabled complex contracts, partnership divisions, and record-keeping across vast distances. Engineering feats included canal construction, water-lifting machines, and fortifications. The Sakia water wheel lifted water efficiently from rivers into irrigation canals. Bridge design relied on knowledge of arches, angles, and load distribution. Cities such as Baghdad and Cairo were laid out with geometric precision. Streets, marketplaces, and public buildings aligned according to careful measurements. Islamic mathematicians also advanced trigonometry. Al-Battani and others refined calculations of sines and tangents. They solved problems related to the positions of celestial bodies and distances between geographic locations. These methods were later applied in navigation, surveying, and astronomy throughout Europe. Calendar reform was another application of mathematics. Accurate observation of lunar and solar cycles was necessary for religious holidays. Intercalation, or the addition of extra days, was calculated mathematically to synchronize lunar months with the solar year. These calculations were precise, often to fractions of a day. Scholars also studied number theory and arithmetic sequences. The properties of prime numbers, perfect numbers, and divisibility were analyzed systematically. These investigations laid the foundation for modern number theory and algebra. Hospitals, observatories, and libraries required precise records. Mathematics enabled scheduling, resource allocation, and architectural design. Calculations ensured that large buildings were structurally sound, and that supplies such as medicine or food were distributed proportionally. The combination of theoretical innovation and practical application characterized medieval Islamic mathematics. Numbers were tools for understanding the universe, governing societies, and supporting commerce. Astronomical tables guided navigation. Algebra solved inheritance and trade problems. Geometry informed architecture and city planning. This knowledge was preserved in manuscripts and translated into Latin, providing the bridge between ancient Greek and Roman thought and the European Renaissance. Without this period of scholarship, much of the mathematical knowledge that shaped modern Europe might have been lost. Islamic scholars did not merely preserve earlier mathematical knowledge. They questioned it, tested it, and extended it into new domains. One of the most influential figures was Thabit ibn Qurra. He worked extensively on number theory, geometry, and astronomy. He studied ratios, proportions, and the properties of numbers, including early work related to amicable numbers. His translations and original contributions shaped how Greek mathematics was understood and expanded. Another major figure was Omar Khayyam. Though widely known as a poet, he was also a mathematician and astronomer. He classified cubic equations and developed geometric methods to solve them. Rather than relying solely on arithmetic procedures, he used intersecting conic sections to find solutions. This approach represented a major advancement in algebraic thinking. Omar Khayyam also contributed to calendar reform. He participated in the creation of the Jalali calendar, which achieved remarkable accuracy by carefully measuring the length of the solar year. Its error rate was smaller than that of the later Gregorian calendar. This achievement required precise astronomical observation and numerical calculation. Astronomy and mathematics continued to reinforce one another. Observatories across the Islamic world gathered extensive data. The Maraga Observatory in present-day Iran became a center for mathematical astronomy. Scholars refined planetary models, introducing geometric techniques that later influenced European astronomy. Trigonometry matured into a fully independent discipline. Islamic mathematicians defined sine, cosine, tangent, and cotangent as numerical functions. They constructed trigonometric tables accurate to several decimal places. These tables were used for astronomy, navigation, and geographic measurement. Spherical trigonometry became essential for determining distances on Earth. This allowed scholars to calculate latitude and longitude with improved accuracy. It also supported long-distance trade and travel across deserts and seas. Mathematics supported cartography. Geographers used numerical calculations to map coastlines, rivers, and trade routes. Coordinates were recorded systematically. Distances between cities were measured using triangulation techniques. Commerce required reliable numerical systems. Merchants relied on decimal arithmetic to calculate profit, loss, and taxation. Complex contracts involved proportional division of investments. Inheritance laws required precise fractional calculations. Islamic legal scholars worked closely with mathematicians. Inheritance laws specified exact shares for heirs. Mathematical formulas ensured fair and consistent distribution. These rules encouraged the development of algebraic methods for real-world problems. Mathematics also played a role in engineering. Canals, dams, and irrigation systems were designed using geometric calculations. Water flow rates were estimated numerically. Agricultural productivity increased as land and water were allocated efficiently. Architectural design reached extraordinary levels of precision. Mosques, madrasas, and palaces followed strict proportional rules. Symmetry governed layout and decoration. Geometric tiling patterns demonstrated deep understanding of angles and transformations. Many of these patterns anticipated concepts later formalized in modern mathematics. Repeated motifs reflected principles of tessellation and symmetry groups. Though expressed visually, these designs were grounded in numerical relationships. The astrolabe became a critical mathematical instrument. It allowed users to calculate time, latitude, and the positions of stars. Astrolabes combined geometry, trigonometry, and astronomy into a single device. They were used by scholars, navigators, and travelers across the Islamic world and Europe. Timekeeping relied on mathematics. Prayer schedules depended on precise solar calculations. Sundials and water clocks required accurate numerical calibration. These systems reinforced the daily importance of mathematical precision. Education emphasized systematic learning. Students memorized multiplication tables, learned algorithms for division and square roots, and practiced algebraic problem solving. Mathematical texts were copied carefully to preserve accuracy. The decimal positional system proved revolutionary. Zero allowed numbers to scale infinitely. Calculations became faster and less error-prone. This system enabled complex accounting, scientific calculation, and engineering planning. The transmission of this knowledge to Europe reshaped Western mathematics. In Spain and Sicily, translation centers converted Arabic texts into Latin. European scholars encountered algebra, trigonometry, and decimal arithmetic. Fibonacci played a central role in this exchange. After studying mathematics in North Africa, he introduced Hindu-Arabic numerals to Europe. His work demonstrated their superiority for trade and calculation. Over time, these numerals replaced Roman numerals across Europe. The influence of Islamic mathematics extended into the Renaissance. Algebra became central to scientific inquiry. Trigonometry supported navigation during the Age of Exploration. Astronomical models informed later thinkers such as Copernicus. Islamic scholars emphasized observation, calculation, and verification. They treated mathematics as a tool for understanding reality. Numbers described motion, structure, and change. This period represents one of the most productive eras in mathematical history. Knowledge flowed across cultures, languages, and continents. Mathematics unified trade, science, law, and architecture. By refining numerical systems and expanding algebraic methods, medieval Islamic scholars transformed mathematics into a universal language. Their work formed the bridge between ancient mathematics and the modern world. The story of numbers continued to evolve, carried forward by calculation, observation, and careful reasoning. Each advancement built upon earlier knowledge, expanding humanity's ability to measure, predict, and understand. Following the gradual transmission of mathematical knowledge from the Islamic world into Europe, a slow but profound transformation began. For centuries, Roman numerals had dominated European record-keeping. They were sufficient for dates, monuments, and basic accounting, but they were poorly suited for multiplication, division, or advanced calculation. As trade expanded across Europe during the late medieval period, these limitations became increasingly apparent. Merchants needed faster, more reliable ways to calculate prices, profits, and currency conversions. Shipbuilders, surveyors, and architects required numerical systems capable of handling complex measurements. The introduction of Hindu, Arabic numerals marked a turning point. This system, which included the digit 0 and positional value, allowed numbers to scale efficiently. Calculations that once required counting boards or written tallies could now be performed directly on paper. One of the earliest and most influential advocates of this system in Europe was Leonardo of Pisa, known as Fibonacci. Born around 1170, Fibonacci grew up in North Africa, where his father worked as a customs official. There, he encountered the mathematical methods used by Islamic scholars and merchants. In 1202, Fibonacci published Liber Abaci, or the Book of Calculation. This text demonstrated how Hindu, Arabic numerals could be used for everyday commercial problems. It included methods for addition, subtraction, multiplication, and division, as well as calculations involving fractions, currency exchange, interest, and profit sharing. The book did not spread instantly. European institutions were slow to abandon Roman numerals. In some cities, the use of Hindu, Arabic numerals was even discouraged due to fears of fraud. Yet merchants recognized their value. Over time, these numerals became standard in trade and finance. Mathematics education in medieval Europe began to change. Universities emerged in Bologna, Paris, and Oxford. Arithmetic and geometry became part of the quadrivium alongside music and astronomy. Students studied numerical relationships, proportions, and basic algebraic reasoning. Algebra entered Europe gradually. Translated works from Arabic introduced symbolic reasoning and equation solving. European scholars adapted these methods, initially expressing algebra rhetorically rather than symbolically. Equations were written in words rather than symbols, but the logical structure remained intact. Commerce drove much of this change. Banking families in Italy, such as those in Florence and Venice, required accurate accounting. Double-entry bookkeeping emerged as a mathematical system for tracking assets and liabilities. This method relied on numerical balance and consistency. Interest calculations became more sophisticated. Merchants calculated compound interest and repayment schedules. Mathematics supported long-distance trade across land and sea. Navigation also benefited from improved numerical methods. Sailors used astronomical observations to determine latitude. Mathematical tables assisted with distance estimation and timekeeping. The ability to calculate accurately reduced risk during long voyages. Measurement systems gradually became standardized. Weights and measures varied widely across regions. Mathematicians and administrators worked to harmonize these systems. Standard units improved fairness in trade and taxation. Geometry influenced architecture. Gothic cathedrals relied on proportional design and precise measurement. Builders used ratios to determine height, span, and stability. Though much knowledge was empirical, numerical reasoning played a central role. Timekeeping advanced as mechanical clocks appeared in European cities. These devices divided the day into regular intervals. Their construction required understanding of gear ratios and cyclical motion. Astronomy remained closely tied to mathematics. European scholars studied translated works of Ptolemy and Islamic astronomers. Planetary tables were refined. Calendrical calculations ensured alignment with religious observances. Mathematical manuscripts circulated slowly. Copying was labor-intensive and error-prone. Yet the gradual spread of numerical knowledge continued. By the late medieval period, Europe had adopted the core elements of modern arithmetic. The decimal system, zero, and algebraic reasoning were becoming established. Mathematics was no longer limited to scholars. It was becoming a practical tool for merchants, builders, and navigators. This transformation laid the groundwork for future scientific advances. Accurate calculation would soon enable new discoveries in physics, astronomy, and engineering. Numbers were becoming central to understanding the natural world. The medieval European adoption of mathematical knowledge was not sudden. It was cumulative, deliberate, and driven by necessity. Trade, navigation, architecture, and administration all demanded better numbers. By embracing numerical precision, Europe prepared itself for the Renaissance. The story of numbers continued quietly reshaping how people measured, recorded, and reasoned. The gradual acceptance of numerical methods prepared Europe for a period of accelerated change. As the medieval world transitioned into the Renaissance, numbers moved from practical tools into instruments of discovery. Mathematics began to describe not only trade and measurement, but nature itself. The invention of the printing press in the mid-15th century played a decisive role. For the first time, mathematical texts could be reproduced accurately and in large numbers. Errors caused by hand copying were reduced. Standard methods spread more quickly across regions. Printed arithmetic manuals appeared throughout Europe. They taught merchants how to calculate interest, exchange currencies, and measure goods. The same numerical rules could now be learned in different cities, creating consistency where once there had been variation. Symbolic notation began to emerge during this period. Earlier algebra relied heavily on words to describe relationships. Gradually, symbols replaced lengthy descriptions. This shift made equations shorter, clearer, and easier to manipulate. The equal sign appeared in the 16th century. Symbols for addition and subtraction became standardized. Letters began to represent unknown quantities. These changes transformed algebra into a flexible language. Mathematics now allowed general solutions rather than isolated examples. A single equation could represent many situations. This abstraction increased the power of numbers. Geometry also evolved. Artists and architects studied mathematical perspective. By using proportional grids and vanishing points, painters created realistic depth. This technique relied on precise numerical relationships between distance and scale. Surveying advanced alongside geometry. Land measurement became more accurate. Governments used mathematics to define borders and collect taxes. Astronomy experienced a mathematical revolution. Observations were recorded numerically rather than descriptively. Planetary motion was measured, compared, and predicted. Tables of values replaced narrative explanations. This shift required precision. Small numerical errors could lead to large discrepancies over time. Mathematical accuracy became essential. The concept of mathematical proof gained importance. Claims were no longer accepted solely on authority. They required logical demonstration. This emphasis on proof strengthened mathematics as a discipline. Trigonometry expanded significantly. Angles and ratios were used to calculate distances indirectly. This was especially useful in navigation and astronomy. Sailors relied on trigonometric tables to determine their position at sea. Latitude could be calculated using the height of celestial bodies. Numbers guided ships across vast oceans. As exploration increased, so did the need for reliable calculation. Maps were drawn using numerical coordinates. Distances were estimated using scale and proportion. Probability emerged gradually from practical problems. Games of chance raised questions about fairness and likelihood. Mathematicians began to analyze outcomes numerically. These early probability studies laid the foundation for statistics. Patterns could be observed across many events. Chance itself became something measurable. Numbers also entered medicine. Physicians recorded symptoms, treatments, and outcomes quantitatively. This allowed comparisons between cases. Population records became more systematic. Births, deaths, and marriages were counted. Governments used these numbers to plan resources and taxation. Timekeeping improved further. Clocks became more accurate. Minutes and seconds gained practical importance. This precision affected navigation, astronomy, and daily life. Mathematics influenced music theory. Notes were understood as numerical ratios. Harmony was described mathematically. This numerical understanding connected sound, space, and motion. Numbers unified diverse fields of knowledge. The Renaissance emphasis on learning encouraged mathematical study. Scholars revisited Greek texts alongside newer works. They compared methods and refined techniques. Mathematics became both a theoretical and practical pursuit. It served artisans and philosophers alike. By the end of this period, numbers were deeply embedded in European thought. They described commerce, art, science, and nature. They offered structure and predictability. This growing confidence in numerical reasoning set the stage for further transformation. Numbers would soon explain motion, force, and change. The language of mathematics was becoming universal. The story of numbers continued not as isolated symbols, but as a system shaping how reality itself was understood. The early modern period witnessed a profound transformation in the way numbers were used and understood. As the Renaissance gave way to the scientific revolution, mathematics expanded beyond commerce and measurement. It began to describe motion, force, and change itself. Scholars across Europe revisited classical texts, translating Greek, Arabic, and Latin works into vernacular languages, preserving ancient knowledge while building upon it. The invention of logarithms in the early 17th century marked a crucial advance. John Napier's tables allowed multiplication and division to be reduced to addition and subtraction, greatly simplifying complex calculations. Mariners, astronomers, and engineers adopted these tables with enthusiasm, making navigation and surveying more precise. Tables of logarithms spread quickly, printed in multiple editions. Their widespread use accelerated scientific discovery. The telescope and microscope transformed observation. Mathematics became essential for interpreting what could now be measured. Galileo used numerical ratios to describe the motion of falling bodies, demonstrating that acceleration was constant and that distances increased according to a predictable sequence. This was a departure from Aristotelian ideas, which described motion qualitatively rather than quantitatively. Measurement replaced conjecture. Numbers described nature with clarity. The study of planetary motion also advanced dramatically. Tycho Brahe recorded thousands of precise observations. Johannes Kepler analyzed these measurements mathematically, deriving his 3 laws of planetary motion. Planets were no longer guided by spheres or mystical harmonies. They moved according to predictable ellipses, governed by measurable ratios of time and distance. The concept of universal law emerged. Isaac Newton synthesized previous discoveries, formulating laws of motion and universal gravitation, expressed in precise mathematical language. Calculus, developed independently by Newton and Leibniz, provided the tools to handle continuous change. Rates of change, acceleration, and forces could now be described numerically. Mathematical modeling became a cornerstone of understanding the physical world. Statistics began to take shape as a discipline. John Grunt and William Petty analyzed population data in London, counting births, deaths, and causes of mortality, revealing patterns that informed public health and urban planning. Probability theory evolved alongside these developments. Blaise Pascal and Pierre de Fermat considered games of chance, translating uncertainty into measurable outcomes, opening the door to modern risk assessment. Economic life increasingly relied on mathematics. Exchange rates, interest, and annuities were calculated using formal rules. Merchants and bankers adopted systematic methods, reducing errors in trade. Measurement became standardized across nations. The meter, kilogram, and second gradually emerged as universal units. Precision facilitated international collaboration. Mathematics influenced engineering profoundly. Bridges, canals, and fortifications were designed with calculated stresses and dimensions. Machines could be constructed with interchangeable parts. Reliability and efficiency depended on exact computation. The study of optics advanced mathematically. René Descartes applied geometry to understand light and reflection, predicting angles, distances, and refraction numerically. Mathematical analysis explained phenomena previously attributed to mystery. Magnetism and electricity became subjects of numerical investigation. Observations were recorded meticulously, experiments repeated to confirm patterns. Laws were expressed as equations. Numbers permeated music theory. Temperament, tuning, and harmonic ratios were analyzed quantitatively, connecting sound with proportion and mathematics. Astronomy continued to evolve. Kepler's tables enabled the prediction of eclipses and planetary alignments. Observatories collected data with increasing accuracy. Mathematical models guided both observation and theory. The scientific method was now inseparable from mathematics. Hypotheses required numerical validation. Experiments were documented with measurements and calculations. Results could be compared across observers and time. Mathematical proof gained central importance. Logic replaced authority. Claims had to be demonstrated numerically, establishing rigor across all disciplines. Trigonometry expanded its practical applications. Surveyors measured land. Sailors calculated latitude and longitude. Architects and engineers designed with precision. The world could now be quantified reliably. Algebra continued to develop. Symbols replaced cumbersome verbal descriptions. Equations represented general relationships. Unknowns could be manipulated with rules rather than examples. The abstraction of algebra enhanced problem solving, making it possible to solve a vast array of situations systematically. Geometry merged with algebra. Descartes' coordinate system connected shapes with equations, facilitating analysis of curves, intersections, and transformations. Mathematical reasoning became more visual and analytical simultaneously. Calculus enabled the modeling of continuously changing quantities. Motion, growth, decay, and flow were all described numerically, from planetary orbits to population dynamics. Differential equations became tools for prediction. Scientists could foresee outcomes based on initial conditions. understanding natural processes as systems. Numbers entered biology. Observations of plants and animals were quantified. Growth rates, lifespans, and population trends could be measured, making life sciences increasingly empirical. Meteorology also benefited. Atmospheric pressure, temperature, and wind patterns were recorded systematically. Mathematical models anticipated seasonal variations. Climates could be compared numerically. Timekeeping improved dramatically. Pendulum clocks measured seconds accurately. Schedules, navigation, and experiments relied on precise timing. Synchronization became possible across cities and nations. Population statistics informed governance. Births, deaths, and marriages were counted. Resources were allocated based on data rather than estimation. Policies became more rational and predictable. Probability and statistics entered commerce. Insurance and gambling were calculated scientifically. Risk could be quantified and managed. Chance itself became a measurable quantity. Negative numbers and zero were fully accepted. Debts and deficits could be represented. Place value systems became universal, expanding the expressive power of calculation. Complex numbers were applied in physics and engineering. Oscillations, waves, and alternating currents relied on them. Mathematics described phenomena that could not be seen directly. Mathematics began to unify diverse disciplines. Physics, astronomy, engineering, economics, biology, and music shared common methods. Numbers became a universal language of the natural world. The printing press enabled rapid dissemination. Mathematical tables, textbooks, and treatises circulated widely. Standard methods spread across Europe and beyond. Knowledge was no longer localized. Computation became routine. Logarithms, trigonometric tables, and algebraic formulas allowed practical calculations. Scientists, merchants, and engineers all benefited. Error checking became possible. Redundant calculation verified results. Precision became a social expectation. Exploration relied increasingly on mathematics. Navigation charts used coordinate grids. Distances and bearings were measured numerically. Maps could now reflect reality with high accuracy. Numbers and measurement shaped everyday life. Trade, construction, astronomy, and governance all depended on calculation. Mathematics was embedded in society at every level. The Renaissance emphasis on learning expanded the audience for mathematics. Students, artisans, and philosophers studied numerical methods. Mathematics became both practical and theoretical. By the late 17th century, numbers had become essential. They described motion, force, probability, and change. They unified previously disparate fields. The precision of calculation transformed understanding. Mathematics had evolved from simple counting into a language of nature. Equations described reality. Laws were expressed numerically. Abstract concepts had tangible consequences. The story of numbers continued, not as isolated discoveries, but as a growing system shaping how humanity understood the world itself. The Enlightenment brought a new focus on reason, on observation, and on the power of numbers. Scholars no longer accepted knowledge solely based on authority. They sought evidence. They demanded precision. They relied on calculation. Mathematics became the language of discovery, of understanding the universe, and of explaining the invisible forces at work in nature. Isaac Newton's work was a turning point. His Principia Mathematica described the laws of motion, of gravity, of planetary attraction, in precise numerical terms. He translated centuries of observation into equations, each number representing a measured or calculable property, each relationship revealing a hidden structure. The world became predictable, describable, and understandable through numbers. Calculus, independently developed by Newton and Leibniz, allowed change itself to be measured. Infinitesimals enabled mathematicians to understand motion, growth, decay, and forces that varied continuously. These methods were applied to the motion of the planets, the flow of fluids, the acceleration of falling bodies. Mathematics no longer measured only static quantities. It became a tool to analyze the dynamics of the world. Leonhard Euler expanded these foundations in the 18th century. He applied analysis to mechanics, to geometry, to combinatorics, and to the emerging field of graph theory. Euler's work demonstrated that complex systems could be understood systematically, that numerical structures could describe natural patterns, and that formulas could uncover relationships hidden to the naked eye. The development of probability theory also advanced significantly. Jacob Bernoulli's Ars Conjectandi formalized the study of chance. Probability was no longer a vague concept. It became a precise tool for decision-making, for understanding games of chance, for predicting population trends, and for assessing risk in commerce and insurance. By analyzing large sets of events, mathematicians could uncover patterns, recognize regularities, and anticipate outcomes with increasing accuracy. Statistics emerged alongside probability. Governments began recording births, deaths, and marriages more systematically. Economists tracked trade and production. Physicians documented symptoms and treatments quantitatively. Numbers became instruments to manage societies, to plan resources, to anticipate epidemics, to regulate commerce. The practical utility of mathematics expanded into everyday life. Astronomy continued to benefit from this numerical revolution. Tables of planetary motion, based on precise calculations, replaced descriptive observations. Observatories recorded data with unprecedented accuracy. The positions of planets, their velocities, their distances from Earth, all were expressed numerically, allowing predictions years, even decades, into the future. The elegance of celestial mechanics reflected the power of mathematical reasoning. Navigation relied increasingly on mathematics. Latitude had long been measurable. Longitude required precise clocks and numerical calculation. Mariners depended on trigonometry, on logarithmic tables, on algebraic methods. Numerical precision meant the difference between safely reaching distant lands or being lost at sea. The expansion of European trade, the voyages of exploration, the mapping of the globe all depended on numbers. Geometry evolved to meet new challenges. Architects applied numerical ratios to design cathedrals, bridges, palaces. Proportion and symmetry were no longer aesthetic choices alone. They became expressions of mathematical understanding. Load-bearing structures were calculated, arches and domes designed with exact measurements. The combination of art and science reflected a new confidence in rational design. Surveying advanced alongside geometry. Land was measured with greater accuracy. Boundaries were established based on numerical calculation. Maps became more reliable, scales more precise. Governments used these measurements to define territories, to administer taxes, to plan infrastructure. Trigonometry expanded further in scope. Angles and ratios were applied to celestial navigation, to artillery calculations, to astronomy and physics. Mathematical tables became indispensable. Sailors, engineers, and astronomers relied on their numbers daily. Mathematics also began to describe phenomena previously considered qualitative. Sound, light, heat, motion. These properties were quantified, expressed numerically. The universe was no longer a set of vague impressions. It became a system of measurable interactions. Education played a key role in spreading these developments. Mathematical texts were printed and widely distributed. Schools emphasized reasoning and calculation. Scholars corresponded across countries, sharing methods, proofs, and discoveries. The Enlightenment ideal that knowledge should be universal and accessible relied on this numerical foundation. Numbers influenced economics as well. Trade networks required accounting, inventory management, exchange rate calculations. Double-entry bookkeeping spread widely. Numerical literacy became essential for merchants, for governments, for anyone participating in commerce. Mathematics entered medicine more deeply. Epidemiology began to take shape. Physicians tracked cases, outcomes, mortality. Public health decisions were informed by statistics. Patterns in disease spread were quantified. Interventions could be planned and measured for effectiveness. Probability and risk analysis extended into social sciences. Voting patterns, market behavior, insurance models. The world's complexities were increasingly described numerically. Mathematical reasoning became the lens through which uncertainty could be understood. The precision of timekeeping continued to improve. Pendulum clocks and later chronometers allowed exact measurement of hours, minutes, and seconds. Experiments in physics, astronomy, and engineering depended on this precision. The interplay between time and mathematics deepened. Music theory incorporated numerical insight. Intervals, harmonics, ratios of sound. Composers used numbers to understand consonance and dissonance. Mathematical relationships explained patterns in sound. Numbers bridged the abstract and the sensory. As the Industrial Revolution approached, the practical applications of mathematics multiplied. Engineers relied on calculations for steam engines, bridges, railways. Predictive models guided manufacturing processes. Efficiency and safety became measurable. Industrial society depended on accurate numerical reasoning. Mathematics became a shared language across disciplines. Natural philosophers, engineers, merchants, astronomers, all used the same principles, symbols, and methods. This unification allowed knowledge to expand exponentially. Each discovery could be shared, verified, and built upon. The concept of mathematical proof strengthened. Arguments were no longer accepted solely on reputation. They required logical demonstration. Deductive reasoning became standard. Mathematics gained intellectual rigor. Its authority came from internal consistency and evidence. The study of calculus, probability, and statistics opened doors to future discoveries. Motion, force, change, all could be expressed numerically. The world could be modeled, predicted, and understood in ways never before possible. Mathematics was no longer confined to the abstract. It was essential to the exploration and comprehension of reality. As the 18th century progressed, mathematicians began exploring patterns in numbers themselves. Prime numbers, ratios, sequences, these were no longer mere curiosities. They became subjects of deep investigation. Mathematicians sought to understand their properties, their distribution, their hidden regularities. Leonard Euler made significant contributions. He explored the infinite, defined functions, linked numbers to geometry and analysis. He showed that numbers had connections far beyond simple counting, that mathematics could reveal hidden structures of reality. The development of complex numbers expanded understanding even further. Imaginary numbers, once considered abstract or nonsensical, became essential in describing oscillations, electrical currents, and later quantum mechanics. They demonstrated that mathematical truth could extend beyond tangible reality, that reasoning alone could uncover structures not immediately visible. The study of combinatorics flourished. Counting arrangements, understanding permutations, patterns emerged in games, social arrangements, and probability. These ideas laid the groundwork for modern computer science. Long before computers existed, mathematicians modeled complex possibilities numerically. Calculus and analysis continued to deepen. Functions were studied. Limits, derivatives, and integrals became tools to describe change. Engineers, physicists, and economists began to apply these concepts. Mathematical formulas predicted motion, population growth, fluid flow, and heat transfer. Mathematics influenced mechanics profoundly. The study of levers, pulleys, and machines became exact. Steam engines were designed using precise calculations. Bridges and buildings were planned using numerical models. Structural failures decreased. Reliability increased. The physical world responded to mathematical reasoning. Astronomy reached new heights. Telescopes improved. Observations became precise to arcseconds. Mathematical models explained planetary motion more accurately than ever. Newtonian mechanics dominated the skies. Celestial bodies moved predictably, governed by laws expressed numerically. Probability theory evolved from games of chance into rigorous analysis. Mathematicians quantified risk in insurance, gambling, and trade. They created formulas to anticipate outcomes. The concept of expected value emerged. Randomness became something measurable, predictable in aggregate. Even chaos could be described probabilistically. Statistics became vital to governance. Census data allowed governments to allocate resources, predict famine, disease, or migration, plan cities, develop infrastructure. Populations were no longer abstract. They were numbers, analyzable, predictable, and manageable. Trigonometry's practical applications expanded. Navigation became more precise, surveying more accurate. Even artillery and military planning relied on angular measurement. Mathematics became inseparable from power, from expansion, from survival. Mathematics also shaped culture. The study of perspective in art relied on ratios and geometry. Music theory explored harmony through frequency ratios. Architecture was guided by proportion and symmetry. Numbers became the silent framework behind beauty, order, and structure. Timekeeping reached new precision. Pendulum clocks evolved into marine chronometers. Accurate time measurement allowed sailors to determine longitude at sea. Trade, exploration, and communication all benefited. The world became increasingly interconnected, underpinned by numerical precision. The Industrial Revolution amplified the importance of mathematics. Engineers relied on formulas to design machinery. Factories were optimized using calculations. Steam, electricity, and mechanization depended on accurate measurement. Efficiency, productivity, and innovation became quantifiable. Mathematical education spread widely. Universities and academies emphasized reasoning and calculation. Textbooks proliferated. Teachers shared standardized methods. Mathematical literacy became a social asset essential for commerce, science, and governance. Number theory advanced significantly. Mathematicians explored divisibility, primes, and modular arithmetic. They discovered surprising relationships, that numbers held secrets far deeper than simple counting. These discoveries revealed the inherent elegance of mathematics, that hidden patterns underlie even the simplest numerical sequences. Algebra evolved into a formal language. Equations could express universal truths. Letters and symbols allowed generalization. Problems that once required lengthy prose could now be written compactly. This abstraction allowed mathematicians to solve complex problems efficiently. The calculus of variations emerged. Optimal paths, minimal surfaces, maximal efficiency. Problems once unsolvable could now be expressed numerically. Engineers and scientists applied these methods to physics, economics, and engineering. The bridge between theory and practice grew stronger. The study of infinite series illuminated convergence and divergence. Summation became more than arithmetic. Infinite sums predicted motion, growth, and behavior. Euler and others demonstrated that infinity could be understood systematically, that numbers were capable of capturing the unending, the immeasurable. The 19th century brought even more rigor. Mathematical analysis became precise. Proofs required completeness, logical consistency. Abstraction increased. Mathematics could describe objects that had never been observed physically. Shapes in higher dimensions, functions without tangible counterparts. Reason alone revealed truths about the universe. Probability theory extended into statistics for science and social studies. Randomness could be described. Experimental outcomes predicted. Error quantified. Observations became data points in a system governed by mathematical laws. Patterns emerged from seeming chaos. Mathematics influenced physics profoundly. Heat, Light, magnetism, and electricity were modeled numerically. Faraday, Maxwell, and others applied equations to describe natural phenomena. Numerical prediction replaced intuition. Theory guided experiment, and experiment refined theory. Engineering benefited from every advancement. Bridges, tunnels, railways, and factories were designed with calculation. Failures decreased. Reliability increased. Societies grew more complex, yet remained manageable through numbers. The industrialized world was built on mathematical foundations. Mathematics began to influence economics more deeply. Numbers were used to model supply and demand, to calculate interest, to forecast prices. Early econometric methods emerged. Merchants and governments relied on numerical reasoning to plan trade and taxation. Markets were no longer blind. They could be analyzed, predicted, understood. The Industrial Revolution demanded even more precise measurements. Steam engines required careful calculations of pressure and temperature. Factories optimized workflow based on timing and output. The productivity of labor and machines became measurable. Efficiency was no longer abstract. It could be quantified, improved, and maximized. Engineering mathematics expanded further. Civil engineers calculated load, stress, and balance. Bridges spanning rivers could be safely constructed. Canals were designed to exact dimensions. Railroads mapped with precision. Every structure relied on numerical planning. Numbers became the silent scaffolding of civilization. The study of probability and statistics matured. Mathematicians began analyzing large populations. Data from censuses, surveys, and experiments were examined. Patterns emerged. Anomalies were discovered. Decisions in public health, urban planning, and finance became data-driven. Chance itself could be understood numerically. Astronomy continued to advance. Observatories cataloged stars, planets, comets. Numbers described orbits with ever-increasing precision. Predicting eclipses, transits, and celestial events relied on rigorous calculation. Mathematics made the heavens predictable. Humanity could navigate, explore, and understand the sky numerically. In parallel, mathematics influenced the natural sciences. Biology began to quantify growth, inheritance of variation. Early statistics helped describe populations of plants, animals, and humans. Experimental results were compared using numbers. Patterns in nature became observable, measurable, consistent. Chemistry relied on numbers to describe reactions. Atomic weights, reaction ratios, and concentrations were calculated. Chemistry moved from alchemy to quantitative science. Precise measurements allowed predictable outcomes. Elements and compounds were understood through numbers. Mathematics inspired early electrical engineering. Ohm, Faraday, and Maxwell used numbers to describe circuits, fields, and waves. Electromagnetism became a system. Equations predicted the behavior of electricity and magnetism. From theory to application, numbers guided invention. The rise of applied mathematics led to more specialized fields. Mechanics, hydraulics, thermodynamics. all relied on numerical laws. Engineers, scientists, and inventors applied mathematics to solve real-world problems. The world became increasingly engineered, guided by calculation. Humanity learned to predict, manipulate, and optimize. Education expanded. Schools taught arithmetic, algebra, and geometry systematically. Textbooks emphasized method, precision, reasoning. Students were trained to think numerically, to approach problems with logic, calculation, and analysis. Mathematical literacy became essential, a tool for survival and progress. Mathematical societies and academies proliferated. Scholars shared methods, discoveries, and proofs. Journals disseminated knowledge. Collaboration accelerated progress. Innovations in one country influenced research across continents. The abstract side of mathematics flourished. Number theory, topology, and analysis explored ideas far from immediate application. Yet these abstractions often later found real-world utility. Complex numbers in electrical circuits, probability in insurance, non-Euclidean geometry in physics. Navigation became increasingly precise. Longitude, latitude, and time could be calculated. Celestial navigation relied on angles, trigonometry, and careful observation. Numbers guided explorers across oceans, through storms, to distant lands. Mathematical skill was literally a tool of survival, discovery, and expansion. The rise of modern finance depended on mathematics. Interest rates, annuities, bonds, and loans were calculated. Investors used probability and statistics to assess risk. The modern economy became inseparable from numerical reasoning. Markets, banks, and governments relied on mathematics to function. Mathematics also influenced technology. Mechanical calculators allowed faster computation. Logarithms simplified complex multiplication and division. Tables of sines, cosines, and logarithms were essential tools for engineers, surveyors, and navigators. Computation became more reliable, more accessible. Numbers enabled human ingenuity to reach further than before. By the 19th century, mathematics had become a universal language. It connected disciplines, commerce, science, art. Engineers, astronomers, physicians, and economists all spoke in numbers. Mathematical precision unified thought across continents. Ideas could be communicated clearly, concisely, without ambiguity. Pure mathematics and applied mathematics grew side by side. Theoretical explorations, practical applications, each informed the other. Problems inspired abstraction. Abstractions solved real problems. The dialogue between theory and application strengthened human understanding. The foundations for modern probability and statistics were laid. Large datasets allowed predictions. Randomness could be described. Patterns could be observed. Decisions in medicine, engineering, finance, and governance became evidence-based. Humanity learned to navigate uncertainty, numerically, methodically, reliably. As the 19th century progressed, mathematics became integral to the emerging field of physics. Newton's laws were refined. Calculus was applied to mechanics. Differential equations described motion, forces, and energy. Every curve, every trajectory, could now be predicted numerically. The behavior of falling bodies, swinging pendulums, and orbiting planets became measurable, calculable, reliable. Electricity and magnetism demanded deeper mathematical insight. Maxwell's equations unified these phenomena. Fields, waves, and currents were described in precise terms. Engineers could design circuits and machines. Predicting voltage and current became a matter of calculation. Mathematics had become the language of energy itself. Optics and light were described mathematically. Lenses and mirrors were designed using precise equations. Refraction, reflection, and dispersion could be calculated. Telescopes and microscopes became instruments of exact science. Astronomers and biologists alike relied on numbers to see further and deeper. The study of heat and thermodynamics evolved. Temperature, pressure, and volume were related through equations. Engines became more efficient. Steam power drove the Industrial Revolution. Mathematical understanding transformed labor, transport, and production. Probability theory matured. Laplace and others extended earlier work. Uncertainty could be quantified. Chance was no longer mysterious. It could be calculated. Gambling, insurance, population studies, and risk analysis were transformed. Mathematics allowed humans to predict outcomes in complex, uncertain situations. Mathematics penetrated the biological sciences. Mendel's laws of inheritance were formulated numerically. Populations of plants and animals could be modeled. Growth rates, genetic ratios, and ecological interactions became measurable. Numbers described life, patterns in nature, relationships invisible to the naked eye. Mathematical notation and theory continued to advance. Set theory emerged. Functions and limits were formalized. Infinity was explored rigorously. Abstract mathematics no longer needed immediate application to justify itself. Yet its future utility was always anticipated. Statistics became essential for governance. Censuses, taxation, and public health relied on numerical analysis. Epidemics could be tracked. Resources allocated efficiently. Governments began to plan societies using numbers. Policies were no longer guesswork. They were evidence-based, measurable, accountable. Mathematics influenced social sciences. Economics, sociology, and psychology began to adopt quantitative methods. Populations, behaviors, and trends were studied numerically. Human society itself could be partially understood through numbers. Predictions about social behavior became possible. Geometry flourished in architecture. Engineers used trigonometry to design bridges, domes, and tunnels. Buildings became taller, longer, and more stable. Numbers ensured safety, symmetry, and beauty. The precision of measurement was now inseparable from artistic achievement. Navigation reached new heights. Longitude could be calculated using time and celestial observation. Latitude was determined with trigonometry and sextants. Explorers could cross oceans with confidence. Trade, migration, and discovery depended on precise numbers. Humans were no longer at the mercy of chance. Numbers guided their journey. Industrial mathematics accelerated innovation. Engineers calculated stresses in machines, beams, and shafts. Factories optimized production through numerical planning. Steam engines, textile machines, and railways were designed mathematically. Efficiency, output, and safety were measurable, predictable, controlled. The printing press enabled wider dissemination of mathematical knowledge. Textbooks, journals, and treatises spread ideas. Scholars in one city could read the latest discoveries from another continent. Standardization increased, methods became widely shared. Mathematical literacy spread faster than ever before. Applied mathematics became essential in navigation, engineering, and astronomy. Ships relied on charts, tables, and calculations. Bridges, aqueducts, and roads were built using formulas. Telescopes and observatories measured positions with precision. Observation combined with calculation, theory combined with practice. Numbers connected the cosmos with human endeavor. Algebra developed further. Symbolic notation simplified calculations. Polynomials, equations, and matrices described relationships. Unknowns could be manipulated systematically. Solutions could be generalized. Applied to many situations, algebra became the bridge between abstract thought and practical problem-solving. Calculus expanded its reach. Derivatives and integrals described rates of change. Motion, growth, and decay could be understood numerically. Physics, engineering, and astronomy all relied on calculus. Every natural process could be represented mathematically. Change itself was now measurable, predictable, describable. The 19th century also saw the rise of mathematical rigor. Proofs became formal, logic-guided reasoning. Mathematical statements required verification. Conjecture and speculation were no longer enough. This emphasis on rigor strengthened the foundations of the discipline. Mathematics became a universal framework for understanding reality. Trigonometry advanced further. Spherical trigonometry enabled accurate navigation on curved surfaces. Astronomers charted the heavens. Surveyors mapped continents. Mathematics allowed humans to comprehend space, distances, and orientation. Probability theory integrated with statistics. Data could be analyzed. Predictions could be made. Outcomes of events could be quantified. Human understanding of uncertainty improved. Mathematics provided the tools to make informed decisions. Mathematics entered medicine. Dosages, mortality rates, and recovery statistics were quantified. Experiments were measured, compared, replicated. Quantitative analysis became essential to medical advancement. Numbers made treatment safer, outcomes clearer, and discoveries reliable. Education spread mathematical knowledge. Universities established dedicated mathematics departments. Students learned both theory and application. Numerical literacy became a hallmark of an educated society. Teachers emphasized reasoning, calculation, and problem-solving. By the end of the century, mathematics had transformed civilization. Commerce, navigation, science, industry, medicine, every field had been shaped by numbers. Society operated with increasing efficiency and precision. Mathematics had become both a tool and a language. It described reality, predicted outcomes, and guided human progress. The story of numbers continued, not as isolated symbols, but as a system shaping human understanding, a force quietly governing the natural world and guiding humanity's journey into the modern age. The story of numbers advanced into the early modern era, a time of invention, discovery, and rapid transformation. Numbers were no longer merely tools for trade, measurement, or navigation. They had become instruments for understanding the world in all its complexity. The Industrial Revolution reshaped Europe and beyond. Factories rose along rivers, powered by steam engines that transformed energy into motion. Gears, pistons, and levers were measured with precision. Mathematics guided the construction of bridges, canals, and railways. Surveying required accuracy. Land was measured in units both familiar and exact. Standardized measurements replaced local variations. The same numerical principles could be applied across cities and nations. Carl Friedrich Gauss explored the deeper properties of numbers. Prime numbers, modular arithmetic, and complex functions revealed hidden structures. His work bridged practical calculation and abstract thought. Algebra became more than solving equations. It became a way to uncover patterns that were universal. Geometry, too, evolved. Mathematicians studied curves, surfaces, and three-dimensional spaces with rigor. Triangles, circles, and parabolas were not mere shapes but expressions of relationships and order. Probability theory developed further. Pierre-Simon Laplace formalized the mathematics of uncertainty. From celestial mechanics to social phenomena, numbers described the likelihood of outcomes. Statistics emerged as a scientific tool. Adolphe Quetelet applied numbers to society, recording births, deaths, crime, and occupation. Patterns emerged in populations, guiding policy and understanding social behavior. The study of heat and motion expanded with the work of Fourier. Complex waveforms could be decomposed into simple components. Vibrations, sound, and thermal behavior were expressed numerically. Electricity and magnetism followed the same trajectory. James Clerk Maxwell demonstrated the power of equations to describe forces invisible to the eye. Astronomy required ever greater numerical precision. Planetary motion, orbits, and celestial distances were calculated with unprecedented accuracy. Mathematical tables, logarithms, and trigonometry were tools for explorers and scientists. Telescopes measured angles, positions, and time. Navigation relied on accurate computation of latitude and longitude. Industrial engineering demanded exact numbers. Gears and machines were tested for tolerance. Steam engines required precise ratios. Railways depended on accurate scheduling, track alignment, and mechanical reliability. The modern world was being built from numbers repeated, applied, and refined. Probability became linked to biology. Charles Darwin's observations of species and variation were quantified. Populations were counted, traits recorded, and evolution understood in statistical terms. Natural selection became a measurable process, numbers revealing the slow work of adaptation. Medical science recorded quantitative data. Symptoms, treatments, recovery rates, and mortality were logged. Epidemiology used numbers to detect patterns of disease. Public health became a field guided by measurement. Commerce relied increasingly on mathematics. Interest calculations, compound growth, annuities, and actuarial tables allowed commerce to expand. Bankers and merchants used numbers to plan, predict, and manage risk. Finance became a system of structured calculation. Telegraphy transformed communication. Sequences of signals, coded numerically, connected cities and continents. Timekeeping became precise. Hours, minutes, and seconds coordinated railways, shipping, and communications. The synchronization of society depended on numerical order. Theoretical mathematics advanced alongside applied work. Set theory and the foundations of analysis were formalized. Infinity, continuity, and abstract structures were explored. Mathematics became a language not only for counting and measuring, but for understanding abstract relationships. By the end of the 19th century, numbers had permeated every aspect of human life, from factories and hospitals to observatories and classrooms. Numbers measured, predicted, and explained. Mathematics was no longer a background tool. It shaped thought, science, and technology. The story of numbers continued, not as isolated symbols, but as a framework through which the modern world could be understood. The mid-20th century brought numbers to the forefront of global events. World War II was not only a conflict of armies, but a war of information, codes, and calculations. Mathematics and statistics played a decisive role in determining outcomes. Cryptography became a battlefield in itself. The German Enigma machine encoded messages with staggering complexity. Breaking these codes required immense numerical reasoning, patience, and ingenuity. Alan Turing and his colleagues at Bletchley Park in England transformed abstract mathematics into practical action. They designed machines later called bombs. Each calculation attempted to reverse the coded messages. Every decoded message saved countless lives. Numbers were not just theoretical concepts, they were tools that directly affected the course of history. Meanwhile, statistical analysis guided the allocation of resources. Operations research emerged as a formal field. Mathematicians calculated optimal strategies for deploying troops, supplies, and aircraft. Fleet movements across the Atlantic, convoy routes, and supply logistics depended on precise numerical planning. Probability and statistical models allowed commanders to anticipate outcomes and reduce uncertainty. Numbers transformed chaos into strategy, enabling more efficient management of military operations. At the same time, numerical methods accelerated. The need to solve differential equations quickly and accurately became urgent. Calculations for ballistics, aerodynamics, and radar required speed and precision. Teams of human computers, mostly women, worked tirelessly, calculating trajectories and firing tables. These computations formed the backbone of technological progress in warfare and engineering. The war also accelerated the development of electronic computing. The Colossus computer in England was one of the first programmable digital machines. It could process data faster than any human mind or mechanical device. Colossus transformed abstract numerical theory into immediate practical applications, influencing strategy and intelligence. In the United States, the Manhattan Project relied heavily on mathematics. Numerical simulations predicted the behavior of nuclear fission. Calculations determined reactor designs, timing of detonation, and the safe handling of fissile material. Physics, engineering, and mathematics worked in concert, producing results that reshaped history. Probability and statistics were refined further. Battlefield simulations, logistics planning, and evaluation of weapon effectiveness all relied on rigorous numerical analysis. Numbers guided decisions that impacted millions of lives and defined strategies in complex environments. Theoretical mathematics continued to evolve alongside applied work. Topology, group theory, and functional analysis found unexpected applications. Quantum mechanics, once abstract, relied on these advanced mathematical structures. Numbers became essential to understanding the smallest constituents of matter, from electrons to atomic nuclei. Applied mathematics expanded into industry and daily life. Operations research influenced supply chains, factory efficiency, and production planning. Statistical methods guided quality control, ensuring consistency and safety. Numbers structured processes, optimized resources, and minimized errors across multiple industries. The development of computers revolutionized the practical use of numbers. ENIAC, one of the earliest electronic computers in the United States, could perform calculations that previously took days in mere hours. Computation moved from manual methods to electronic precision. Numbers flowed seamlessly from theory into application, shaping both industry and research. Education adapted to this numerical age. Universities introduced courses on applied mathematics, statistics, and computational techniques. Students learned to translate abstract equations into real-world results. Mathematics became a universal language, taught across countries, cultures, and languages. Post-war, an explosion of data reshaped society. Population studies, economics, and social sciences increasingly relied on numbers. Governments conducted detailed censuses, analyzed health data, and planned urban infrastructure. Numerical insight guided policies, public health initiatives, and economic planning. Numbers penetrated the arts and humanities as well. Computer-generated music explored mathematical harmony. Digital simulations of architecture relied on numerical precision. Even literature and linguistics analyzed patterns using statistical methods. Mathematics became a bridge between creativity, structure, and understanding. By the 1950s, modern computing had firmly established itself. Numbers moved effortlessly between theoretical research and practical application. The boundaries between abstract mathematics and real-world use blurred. From factories to laboratories, classrooms to observatories, numbers governed operations and thought. Numbers have fully integrated into human life. They guided science, warfare, industry, governance, and art. From the abacus to electronic computers, numbers had evolved into a universal language. A language that described, predicted, and shaped the modern world. The story of numbers continued, expanding in scope, precision, and power. Numbers were no longer passive tools. They were active instruments of understanding and progress. As the world moved beyond World War II, the role of numbers expanded exponentially. The invention of transistors in the late 1940s transformed computing. Tiny semiconductors controlled electrical currents. Binary logic of zeros and ones became the foundation of every calculation. By the 1960s, mainframe computers had become central to research, industry, and government. Numbers were processed faster, more accurately, and in far greater quantity than ever before. Computers enabled scientists to explore previously unimaginable problems, simulating complex phenomena and processing massive datasets. Numerical analysis evolved rapidly in mathematics. Algorithms became increasingly sophisticated. Differential equations, optimization problems, and simulations of physical systems could be solved with unprecedented speed. Climate modeling, aerodynamics, and structural analysis all relied on numerical precision. The 1970s and 1980s saw the rise of personal computing. Numbers were no longer confined to laboratories. They entered offices, schools, and eventually homes. Students learned algebra and programming on desktop computers. Scientists modeled chemical reactions. Businesses tracked inventory, production, and logistics using numerical data. Numbers became practical tools for everyday life. Statistics and probability gained new importance. Economists developed models to predict economic growth and market behavior. Epidemiologists analyzed disease outbreaks using quantitative methods. Graphs, tables, and charts translated raw numbers into actionable insights. Governments used these analyses for policy, resource allocation, and public health planning. Cryptography entered a digital era. Numbers became essential for secure communication. Public key cryptography relied on enormous prime numbers. Messages could be encrypted, transmitted, and decrypted only with precise numerical keys. Digital security, commerce, and private communications all depended on these methods. The rise of the Internet in the 1990s transformed the numerical landscape further. Vast amounts of data flowed continuously across networks. Servers, databases, and networks processed information in real time. Transactions, communications, and research all depended on numerical accuracy and speed. Abstract mathematics continued to evolve alongside applied methods. Topology, algebraic geometry, and number theory found applications in computing, physics, and cryptography. Mathematicians proved theorems, discovered patterns, and revealed structures that governed both natural and artificial systems. Data science emerged as a major discipline. Large datasets were analyzed to discover trends, predict behavior, and optimize systems. Algorithms identified patterns invisible to human perception. Numbers translated complex information into understanding and insight. Machine learning and artificial intelligence transformed the role of numbers yet again. Neural networks relied on matrix operations, probability, and optimization. Self-driving vehicles, predictive models, and automated systems operated entirely through numerical computation. Numbers became instruments for decision-making, prediction, and automation. Numbers influenced culture and creativity. Digital media, audio, and video relied on numerical encoding. Streaming platforms delivered content through precise algorithms. Music, film, and games were all guided by mathematical modeling, allowing creativity to be expressed through structured numerical frameworks. The global economy depended on numbers more than ever. Financial markets tracked prices, risk, and probabilities in real time. Mathematical models guided investment strategies, hedging, and economic policy. Algorithms executed millions of trades every second based on numerical analysis. Science increasingly relied on numerical simulation. Particle physics, genomics, and climate modeling depended on computational models. Complex systems were simulated, studied, and predicted through numerical methods. Population studies and urban planning utilized demographic statistics to guide policy and infrastructure development. Medicine advanced through numbers. Clinical trials, statistical analysis, and medical imaging depended on precision. Imaging technologies converted physical signals into numerical data for diagnosis and treatment planning. Mathematical modeling accelerated drug development, surgical planning, and medical research. Education transformed alongside technological advancement. Interactive learning, simulations, and digital tools allowed students to explore mathematics, physics, and computational concepts. Quantitative reasoning, logic, and precision became central to the learning process. Entertainment relied increasingly on numbers. Video games, simulations, and digital effects were based on mathematical modeling. Physics engines calculated movement and interaction in real time. Animation, virtual reality, and digital art used algorithms to create immersive experiences. Throughout the modern era, numbers provided clarity in an increasingly complex world. They measured, predicted, and guided. From engineering to scientific research, from commerce to creative industries, numbers structured reality. They enabled humanity to translate theory into tangible results, to manage complexity, and to explore new frontiers. By the early 21st century, numbers had permeated every aspect of human existence. Artificial intelligence, big data, and quantum computing expanded the possibilities of numerical application. Researchers modeled complex systems, optimized networks, and predicted outcomes at unprecedented scales. The story of numbers, now spanning thousands of years, had evolved from simple counting to the backbone of modern civilization. From ancient abbaci and tally marks to digital computation, numerical reasoning shaped societies, discoveries, and daily life. Numbers were both a language and an instrument, bridging imagination and reality, theory and application. The legacy of numerical development continued into every aspect of the 21st century. Computing infrastructure, financial systems, scientific research, and global communications all depended on precision, reliability, and speed of numerical methods. Numbers guided exploration, innovation, and understanding across all human endeavors. And as the journey of numbers continued, their influence became universal. They linked the ancient with the modern, the practical with the abstract, the simple with the complex. Every computation, every equation, every calculation represented a continuation of a story that had begun thousands of years ago. Numbers had become instruments for understanding, predicting, and shaping the world. They connected generations, civilizations, and technologies. From counting grains of wheat to analyzing quantum particles, numbers told the story of human curiosity, ingenuity, and progress. The story of numbers in the modern era was vast, intricate, and unending. It had grown from tools for trade and measurement to a universal framework governing knowledge, technology, and society. Every field, every discipline, and every culture had been touched by the silent power of numbers. This modern chapter of numbers set the stage for future generations. They would continue to explore, to calculate, and to expand the reach of mathematics. Numbers had become not just a tool, but a language of discovery, an instrument of civilization, and a foundation for the unknown. The story of numbers continued, building on millennia of human thought, experiment, and application. From simple beginnings to the vast digital and scientific landscape of the 21st century, numbers remained a universal and enduring force. As the 21st century progressed, numbers became the silent force behind nearly every aspect of human life. The proliferation of digital technologies transformed society. Computers, smartphones, and networks allowed information to flow at speeds and volumes unimaginable just decades before. Data became a resource as vital as water or energy. Every transaction, every communication, every interaction could be captured, quantified, and analyzed. Governments, corporations, and researchers relied on these numbers to make decisions, forecast trends, and optimize outcomes. The rise of the internet created an interconnected web of numerical information. Web traffic, search queries, and user behavior were tracked and stored in massive databases. Algorithms processed this information continuously, detecting patterns, predicting preferences, and delivering insights. Financial systems depended on numbers more than ever. Markets operated with algorithms that monitored risk, price, and demand in real time. Investment strategies, currency exchanges, and trade flows were all guided by numerical models. The speed and precision of computation transformed economies into highly responsive, data-driven networks. Scientific research experienced a parallel transformation. Simulations and numerical models replaced or augmented physical experiments in many fields. Climate science, particle physics, and genomics all relied on the power of numbers to explore phenomena too vast, too small, or too complex to observe directly. High-performance computing enabled breakthroughs across disciplines. Weather models predicted storms with greater accuracy. Epidemiological studies tracked diseases and forecasted outbreaks. Astronomers mapped the cosmos, using precise calculations to chart the movements of celestial bodies millions of light-years away. Artificial intelligence and machine learning introduced a new era of numerical reasoning. Neural networks, trained on enormous datasets, learned to recognize patterns, translate languages, and make decisions. Automation reshaped industries, from manufacturing to logistics to healthcare, all powered by complex numerical algorithms. Data science became a defining field. Analysts processed millions of records to uncover trends invisible to human perception. Numbers revealed relationships, probabilities, and correlations, informing policies, business strategies, and scientific exploration. In medicine, numbers became essential for precision and discovery. Clinical trials, diagnostic imaging, and treatment planning all depended on quantitative analysis. Genomic sequencing transformed biology into a field dominated by computational models and statistical insight. Numerical precision allowed researchers to understand the structure and function of life itself. Education adapted to the digital and numerical age. Interactive platforms allowed students to explore mathematics, physics, and computer science with unprecedented engagement. Algorithms could tailor lessons to individual learning patterns, providing feedback informed by quantitative metrics. Numbers penetrated culture and creativity. Digital media, music, film, and video games relied on numerical frameworks for design, animation, and interactivity. Mathematical principles guided the creation of virtual worlds, soundscapes, and cinematic effects. In governance and urban planning, numbers dictated decisions on infrastructure, resource allocation, and public policy. Census data, economic statistics, and environmental measurements informed city planning, disaster response, and sustainability initiatives. Every policy, every project, every plan depended on precise numerical reasoning. Numbers also shaped personal life. Navigation systems, fitness trackers, and financial apps translated daily activity into data. From monitoring health to managing time, numbers provided structure, guidance, and insight. In industry, numbers guided automation, quality control, and supply chain management. Manufacturing, logistics, and energy distribution all relied on models and simulations. Efficiency and safety depended on precision, calculation, and constant monitoring. Throughout this era, numbers became increasingly abstract yet deeply practical. Advanced mathematics, including topology, complex systems theory, and computational geometry, found applications in artificial intelligence, computer graphics, and network analysis. Theoretical insights guided practical tools, and practical problems inspired new theory. By the early decades of the 21st century, numbers had become a universal language. They connected disciplines, cultures, and technologies. They transformed society from one based on intuition and observation into one governed by calculation, prediction, and measurement. The story of numbers now encompassed digital networks, artificial intelligence, computational modeling, and global communication. From the ancient abacus to quantum computing, numbers had become instruments of discovery, understanding, and progress. They were no longer mere tools. They were a lens through which the modern world could be understood and shaped. Human civilization relied on numbers as never before. The smallest calculations could influence global markets, medical treatments, or scientific breakthroughs. The precision and speed of computation enabled endeavors that were impossible in previous centuries. As society advanced, numbers guided decisions that affected billions. Population studies, climate projections, and economic forecasts all depended on accurate data and careful analysis. Statistical reasoning and probability theory became essential not only for scientists and policymakers, but for the functioning of daily life. Numbers influenced creativity and expression. Digital art, procedural music, and interactive storytelling all drew upon mathematical principles. Algorithms created patterns, sequences, and rhythms, merging human imagination with numerical logic. In the realm of science, numbers continued to expand the boundaries of understanding. Quantum computing promised new ways to model and manipulate reality. Simulations allowed experimentation with conditions that were impossible or dangerous to replicate physically. Even in everyday life, numbers quietly governed experience. Transportation schedules, communication networks, financial transactions, and entertainment platforms all relied on numerical precision. Numbers provided consistency, predictability, and reliability in an increasingly complex world. The legacy of centuries of mathematical development was now fully integrated into the fabric of society. Numbers shaped thought, guided innovation, and connected generations. They were simultaneously abstract and concrete, theoretical and applied, universal and personal. By mid-21st century, numbers had become inseparable from human progress. Computation, analysis, and prediction formed the foundation of decision-making at every scale. From global policy to individual choices, numbers informed understanding, efficiency, and creativity. The story of numbers had reached a stage where their influence extended to nearly every dimension of life. Technology, science, society, and culture all depended on them. The ancient pursuit of counting and calculation had evolved into a comprehensive framework for interpreting reality. Humanity had entered an era where numbers were the silent architects of the modern world. They guided exploration, structured knowledge, and enabled innovation across all domains. Numbers had become instruments of understanding, prediction, and transformation. And as the digital age unfolded, the story of numbers continued. They connected the achievements of the past with the potential of the future. From the abacus to artificial intelligence, from tally marks to algorithms, numbers shaped civilization and guided humanity's ongoing journey of discovery. As the 21st century progressed further, numbers became the backbone of an era defined by data. The amount of information generated by humans, machines, and networks grew exponentially. Every click, every sensor, every digital transaction contributed to a vast ocean of numerical data. Governments and corporations sought to organize and understand this information. Databases expanded to unimaginable size, capable of storing billions of records. Data scientists developed algorithms to detect patterns, make predictions, and extract meaning from the flood of numbers. Artificial intelligence transformed the way numbers were applied. Machine learning models, fed with vast datasets, could recognize images, translate languages, and predict outcomes. Numbers were no longer passive. They were active agents of insight. Neural networks processed millions of inputs simultaneously. Each layer of computation refined the output, discovering structures hidden from human observation. Numbers guided the training of these systems, adjusting weights, biases, and connections to optimize results. In healthcare, numbers revolutionized diagnosis and treatment. Medical imaging, genomics, and predictive analytics relied on precise numerical models. Researchers analyzed massive datasets of patient information to identify trends and correlations. Numbers helped doctors tailor treatments to individual patients, improving outcomes and saving lives. In environmental science, numbers provided clarity amid complexity. Climate models combined physics, chemistry, and observational data into predictive frameworks. Numerical simulations projected weather, monitored ecosystems, and forecasted the impact of human activity on the planet. Numbers quantified uncertainty, probability, and risk, informing policy decisions and global initiatives. The financial world depended more than ever on numerical precision. High-frequency trading, algorithmic investment strategies, and risk management were driven by real-time data. Millions of transactions occurred each second, guided by models that calculated probability, volatility, and correlations. In education, numbers reshaped learning. Adaptive platforms measured student performance, identified weaknesses, and adjusted curricula. Mathematics, coding, and analytical reasoning became essential skills, cultivated through data-informed instruction. Scientific exploration reached new heights through numerical modeling. Particle physics, cosmology, and genomics relied on computations that were impossible without modern computing power. Simulations allowed researchers to test hypotheses, explore extreme conditions, and predict phenomena before observation. Digital communication depended on numbers at every level. Encoding, compression, and transmission of data relied on mathematical principles. From emails to streaming media, numbers ensured accuracy, fidelity, and efficiency. Artificial intelligence expanded into creative domains. Procedural music, generative art, and automated writing demonstrated the intersection of human imagination and numerical logic. Algorithms translated abstract numerical patterns into sound, image, and text, producing novel creations. Cybersecurity became a field defined by numbers. Encryption algorithms relied on prime numbers, modular arithmetic, and probability theory. Digital systems were secured through computations that protected information, privacy, and commerce. Urban life increasingly depended on numerical systems. Smart cities used sensors to monitor traffic, energy usage, and public services. Numbers guided decisions about infrastructure, logistics, and safety. Data-driven insights enabled cities to respond to events in real time, optimizing efficiency and sustainability. In transportation, numerical models guided everything from traffic flow to autonomous vehicles. Algorithms calculated optimal routes, predicted congestion, and improved safety. Numbers translated complex, dynamic systems into actionable plans, ensuring smooth operation. Communication networks relied on numerical optimization. Bandwidth allocation, packet routing, and error correction depended on precise calculations. From local networks to global internet infrastructure, numbers enabled instantaneous, reliable connections. In commerce, numbers influenced marketing, sales, and inventory management. Predictive models analyzed consumer behavior, optimizing pricing, stock levels, and logistics. Algorithms balanced supply and demand, reducing waste and improving efficiency. Scientific research continued to blur the lines between theory and application. Computational models in biology, chemistry, and physics allowed exploration of systems too complex for direct experimentation. Numbers enabled virtual laboratories, where hypotheses could be tested with unprecedented precision. Data visualization became essential for understanding complexity. Graphs, heat maps, and multidimensional plots transformed raw numbers into insights accessible to decision makers. Numbers communicated patterns, anomalies, and trends in a language both precise and intuitive. The entertainment industry embraced numbers in every dimension. Streaming platforms, recommendation systems, and content analytics relied on algorithms. Numerical analysis guided production, marketing, and delivery, shaping what audiences experienced and how. Social sciences increasingly depended on numerical rigor. Survey analysis, behavioral modeling, and demographic studies relied on statistical methods. Numbers provided insight into human behavior, social trends, and policy outcomes. Environmental monitoring expanded through numerical methods. Satellite imagery, sensor networks, and predictive models quantified changes in climate, ecosystems, and biodiversity. Numbers translated natural phenomena into actionable understanding. In manufacturing, precision and automation were guided entirely by numbers. Robotic assembly lines, process optimization, and quality control relied on continuous measurement and adjustment. Numerical feedback loops ensured consistent production and efficiency. The field of mathematics itself continued to expand in parallel. Algebraic geometry, topology, and combinatorics found applications in machine learning, cryptography, and network science. Abstract theory became increasingly intertwined with practical computation, guiding the design of algorithms and systems. By the second decade of the 21st century, numbers had become pervasive. From the global economy to individual decision-making, from scientific exploration to creative expression, numbers informed, guided, and structured reality. They were no longer merely descriptive. They were predictive, prescriptive, and transformative. The story of numbers in this era highlighted their dual nature. They were both tools of human imagination and instruments of objective analysis. They enabled understanding across scales, from the microscopic to the global. Every sector of society, every dimension of life depended on the quiet power of numbers. Healthcare, governance, commerce, science, and culture all relied on precise calculation and analysis. Numbers shaped decisions, revealed patterns, and guided action. The evolution of numbers had reached a stage where they were inseparable from human progress. They connected centuries of knowledge, from ancient counting methods to advanced computation. They bridged theory and practice, abstract reasoning and real-world application. By the mid-21st century, humanity's reliance on numbers was profound. Artificial intelligence, big data analytics, and global information networks created a world where numerical understanding defined possibility. Numbers allowed humans to explore, innovate, and manage complexity on an unprecedented scale. The story of numbers had grown from simple tallies to the architecture of the digital world. From commerce to science, from exploration to entertainment, numbers guided every facet of civilization. Their influence was silent yet omnipresent, shaping the modern age in subtle, indispensable ways. And so, by the end of segment 10b, numbers had become the language of understanding, discovery, and human endeavor. They connected past achievements with present innovation, forming the foundation of society in the digital era. And numbers have become the fabric of daily life, woven into every system and structure. From cities to industries, from research laboratories to households, numbers dictated patterns, processes, and progress. The rise of the Internet of Things connected billions of devices, each generating streams of data. Sensors in homes monitored energy usage, temperature, and safety. Numbers guided automation, adjusting environments in real time to optimize comfort and efficiency. Transportation had become increasingly numerical. Self-driving vehicles relied on complex algorithms to navigate streets safely. Traffic flows were managed through predictive models, minimizing congestion and accidents. Logistics networks calculated optimal routes for delivery fleets, reducing fuel consumption and travel time. Healthcare advanced further through precision medicine. Genomic data, electronic health records, and wearable devices produced unprecedented quantities of information. Statistical models and machine learning algorithms identified risk factors, suggested preventive measures, and guided treatment plans. Numbers became the bridge between diagnosis and personalized care, saving lives and improving outcomes. Education evolved in parallel. Adaptive learning platforms measured comprehension, engagement, and retention. Curricula were personalized based on numerical feedback, allowing students to progress at their own pace. Mathematical reasoning, coding, and data literacy became central to learning, preparing generations for a numerically driven world. In science, numbers had unlocked new frontiers. Astronomy mapped the cosmos with extraordinary precision, using data from satellites, telescopes, and probes. Particle physics relied on vast numerical simulations to understand the fundamental components of matter. Climate science modeled Earth systems, predicting weather patterns, natural disasters, and long-term environmental changes with increasing accuracy. Economics and finance became inseparable from quantitative analysis. High-speed trading, risk modeling, and global market analysis depended on numerical computation. Artificial intelligence evaluated investment strategies, analyzed trends, and executed transactions with unprecedented speed and precision. The arts embraced numbers as well. Computer-generated compositions, visual art, and literature explored mathematical structures and algorithmic creativity. Music used fractals and ratios to produce new harmonies. Generative design created structures impossible for human hands alone. Numbers guided aesthetic expression, transforming imagination into digital reality. Governance and policymaking relied heavily on data. Population demographics, resource allocation, and infrastructure planning depended on statistical models. Policy decisions were informed by predictive analysis, optimizing public health, education, and urban development. Numbers provided clarity in complex, interconnected systems, reducing uncertainty and guiding collective action. Communication systems operated entirely on numerical principles. Digital encoding, encryption, and transmission allowed secure, instantaneous communication across the globe. Every message, every transaction, every interaction depended on precise calculations. Artificial intelligence permeated nearly every field. From natural language processing to medical diagnostics, from climate modeling to industrial automation, AI transformed data into insight. Neural networks, deep learning models, and reinforcement learning algorithms relied on complex numerical computations to function effectively. The global economy had become a network of numbers. Trade, finance, logistics, and production were coordinated through digital systems that depended on accurate, real-time numerical analysis. Numbers dictated pricing, supply, demand, and risk, shaping the everyday lives of billions. Even cultural phenomena were quantified. Social media, streaming platforms, and digital content analyzed engagement, preference, and behavior through numerical feedback. Algorithms predicted trends, guided recommendations, and shaped experiences in subtle yet pervasive ways. Scientific research increasingly relied on simulations. Experiments that were once costly or impossible could now be conducted virtually. Numerical models allowed exploration of extreme environments, complex chemical reactions, and cosmic phenomena. Urban development embraced numbers to create smart cities. Traffic, energy, water, and waste systems were monitored continuously. Data-driven management optimized efficiency and sustainability, making urban life smoother and more predictable. In space exploration, numbers were critical. Orbital calculations, trajectory planning, and interplanetary navigation depended entirely on precise computation. Missions to Mars, asteroids, and beyond were possible because mathematics translated ambition into actionable reality. The integration of numbers into society had created a world where human understanding expanded continuously. Quantitative methods transformed knowledge, enabling predictions, guiding decisions, and fostering innovation. From the smallest cellular analysis to the largest global system, numbers provided structure, coherence, and insight. As artificial intelligence matured, it began assisting humans in interpreting and applying numbers at scale. Complex systems in energy, medicine, and transportation were monitored and optimized in real time. Patterns invisible to individual observation became apparent through the analytical lens of computation. The digital age had blurred the line between human reasoning and numerical analysis. Numbers were no longer confined to academia or industry. They permeated culture, art, governance, and daily living. They enabled communication across continents, coordination across networks, and collaboration across disciplines. In essence, numbers had become a universal language, a language that transcended borders, disciplines, and eras. It connected ancient tally marks to modern quantum computations, from the abacus to artificial intelligence. The journey of numbers, from counting, measuring, and trading, through centuries of human inquiry, to the sophisticated systems of today, had reached a remarkable culmination. They were instruments of knowledge, tools of discovery, and frameworks for understanding the modern world. And as our journey along the story of numbers draws to a gentle close, feel your mind settle, your thoughts drift. Imagine the centuries of discovery stretching behind you. The abaci, the counting boards, the mechanical calculators, the computers, the satellites, the AI systems, all part of a continuum, a human endeavor expressed through numbers. There is no need to hold on to every equation or calculation. Only the sense of continuity, the quiet power of numerical understanding shaping civilization. From ancient merchants to modern scientists, from mathematicians in dusty study halls to engineers in high-tech labs, numbers connected them all, silently, persistently, profoundly. If you've enjoyed this journey through the evolution of numbers, consider leaving a thought, a reflection, or simply rest in the knowledge of this vast story. The legacy of human understanding, carried forward by the quiet, constant rhythm of numbers. For now, let the day settle behind you. Let your breathing slow, steady, effortless. Drift into rest, carried by the timeless march of numbers, the language that shapes our world and our minds. Sleep well, dream deeply, and may your night be as orderly, infinite, and gentle as the world of numbers itself.